What? Hi, I'm your neighbor. I feel bad about all this renovation noise we're making, so I brought you some cupcakes. Do those have peanuts in them? No. Do they have wheat in them? Yes. Are you trying to kill me? Oh, I'm so sorry. Do you have allergies? I don't. Are you trying to kill me? No? He's on to us. When I was a kid, I used to write secret messages to my friend using an almost unbreakable code. It's probably been long enough that I can show you how it works. Basically, you replace every letter in the alphabet with another letter. But the way we did it was especially clever. Take the letter Z and substitute it for A. Then take Y and substitute it for B. C becomes X, D becomes W, and so on. This code blew our brains out of our skulls. We could write messages to each other and nobody would know what we were saying. Now looking back, the code had a few weaknesses. For example, we only ever wrote messages in code to each other when we were together, sitting together, next to each other. Also, growing up with a pencil and a piece of paper could figure it out pretty quickly. A baby could have figured it out. And I'm not a baby, you are. There are more sophisticated ways to write codes with your friends. You can make a code that's relatively hard to crack using, you guessed it, linear algebra. Let's use matrix multiplication to encode the following useful message. University students take note. Grandma, send money. The first thing to do is to assign numbers to all of the characters in the message, including spaces. I'm going to do this the simplest way, just letting A equals 0, B equals 1, C equals 2, and so on, but I'll also include that a space is 26. All of the secret work is done by an encoding matrix. Once you decide the dimensions of the encoding matrix, the rest will sort itself out. For this message, I'm going to use a 3x3 encoding matrix that looks like this. The only two requirements for our encoding matrix are 1, that it's invertible, and 2, that the determinant has no common factors with the number of numbers in our scheme. So in my scheme, I had A equals 0 all the way to a space equals 26. That's 27 numbers. I have to have a matrix with a determinant that has no common factors with 27. Now I could bang my head against a wall and try to think of such a matrix, or I could just add a couple numbers to my scheme so that I end up with a prime number. The closest prime to 27 is 29, so I'm going to add 2 characters to my scheme. I'm going to add a period, which will be the number 27, and a comma, which is 28. Now I have 29 numbers. And I think I could use this matrix as my encoding matrix. Okay, with the encoding matrix in hand, now I need to put my message into a matrix. Since my encoding matrix is 3x3, my message matrix has to have 3 rows. Now, my message has 18 characters, including spaces. So that means my message matrix should have 6 columns, like this. Now I'm going to write the numbers corresponding to my message as the columns of the message matrix. Now you do the matrix multiplication as we usually do to get the encoded message here. Okay, so I've encoded a message. Now how can Grandma decode it? All she needs is the inverse of the encoding matrix. I don't have time to cover matrix inversion here, so I'll put a link in the description for a tool that will invert matrices for you. However, with the inverse of your encoding matrix and the encoded message, your grandma can then decode the message and respond. Now you know how to encode messages using matrix multiplication and decode them. Of course, there are more secure ways of sending coded messages, but this one is fun and pretty simple to do. This particular method was invented in 1929 by a mathematician named Lester Hill. Since it's fully linear, anyone who has a single decoded column of the encoded message can use this to solve a system of linear equations. However, if you combine this linear method with some non-linearity, then even Bradley the hacker won't be able to crack it. Even though this algorithm comes with security concerns, it can still be included as part of a more complicated encoding scheme. Plus, it's fun to do with your friends or your grandma. I left an encoded message for all of you in the description below, together with the encoding matrix, which you'll have to invert. This marks the end of my little series on applications of linear algebra. In the future, you can look forward to a wide range of topics on mathematics from the simple to the complicated. So subscribe to stay tuned. And until next time, keep it linear.